Welcome back, guys, to Chem Talk. Today on Chem Talk, we are going to move from the small, unseen world of atoms and molecules to the larger world where we can actually see, feel, touch these different compounds that we have been talking about. And this is one of the most fundamental concepts in chemistry. It's what makes chemistry practical, that we can able to do it in the lab, and that is called the mole. So come along with me today and pay close attention and take really good notes. Okay, quick review. Atomic mass. Remember, atomic mass is the mass of a single atom of any given element. It's been based on the mass of carbon-12. Okay, we talked about that already. But atomic mass refers to the weight of a single atom. We can talk, for example, we talk about hydrogen. It weighs 1.01 AMUs, atomic mass unit, or oxygen, which we can round to 16.00 AMUs. Related to this is the idea of a formula mass, and the formula mass is simply the sum of all the atomic masses of an atom in a compound. So if we take water, for example, H2O, to figure out the formula mass, we take 2 hydrogen, so it's 1.01 times 2, so 2.02, plus 1 oxygen, 16, gives a total mass of 18.02 AMU. Now, if I threw 1 molecule of water on you, you would never feel it. Okay? So today we're going to go moving from these really small quantities into something more measurable. And just to give you an idea, don't copy this down, but atomic mass and formula mass are really not very useful for practical applications. Talking about 1 atom or 1 molecule doesn't do us much good. So what we need to do is to find a way to relate these atomic masses for the single atom or single molecule, single compound, to grams, because we can feel grams, we can measure grams. And the way we do that is something called Avogadro's number, or referred to also as a mole of a substance. Avogadro's number is simply a measurement of the amount of particles in a substance. It's actual numerical value. Okay, it was named in honor of a scientist, Amedeo Avogadro, which we'll talk about here in just a little bit. Avogadro's number is 6.02 times 10 to the 23rd. Really big number. Okay, what that means is that in 12 grams of carbon-12, we find 6.02 times 10 to the 23rd particles. So if we are able to measure out 12 grams of it and count each of those particles, we'd find there's 6.02 times 10 to the 23. Write that number out. See how big it is. It is absolutely huge. Okay? But this is a standard measurement, which means that this holds true not only for carbon, but for all elements. So if we have a mole of any substance, it's going to contain 6.02 times 10 to the 23rd. Okay, mole and 6.02 times 10 to the 23rd are kind of the same numerical value. It's kind of like saying, instead of saying I have 12 eggs, you'll say I have 1 dozen eggs. Instead of saying I have a 4,000-pound pickup truck, you say I have a 2-ton pickup truck. They're the same numerical values, we just express them a little differently. Why? Because if we have to say 6.02 times 10 to the 23rd a lot, it gets a bit of a tongue twister. So we say I have a mole of this. Okay, so the mole, when we use the term mole, it refers to a substance containing an Avogadro's number of particles. So any particle that contains, or any mass that contains 6.02 times 10 to the 23rd particles, we say we have a mole of it. Okay, mole is Latin for heap or pile. Please don't get its abbreviation of MOL confused with molecule. We don't have abbreviation for molecule, but we do for mole. Okay, the nice thing about once we have the mole, it can let us do a bunch of conversions. Now we have a connection between the number of particles and number of moles. We know that in 1 mole of any substance, there's 6.02 times 10 to the 23rd particles. Okay, this also is going to help us establish a relationship between atomic mass and grams. So we can go from this really small AMU unit up to grams and do some practical chemistry here in our classroom even. Just a little fun fact. How big is a mole? Let's say we had a mole of pennies, 6.02 times 10 to the 23rd. How much money would that be? Well, we have to do a little factor labeling. We're going back to factor labeling again. We start with what we're given, 6.02 times 10 to the 23rd, and we know that in $1 there are 100 pennies. Okay, so that is 6.02 times 10 to the $21. That's a lot of money. Now, imagine we spread that over the whole world population, which currently is just over 7 billion. We'll make it easy and say 7 billion. Take 6.02 times 10 to the 21 divided by 7 billion. That means each person would get 8.6 times 10 to the $13. That's a lot of money. But imagine if everybody had that much money, how much a single donut would cost. If everybody's equal, it's not as much as we think. All right, let's get going. This is Amedeo Avogadro. To me, he looks like a grasshopper. He was an Italian physicist and professor. And he originally worked with gases and came up with what is known as Avogadro's law or Avogadro's principle. And what this work at gases did is it laid the foundation for the relationship between an atom's weight and the number of atoms in that particle. So it allowed us to get to this concept of the mole and to go, once again, go from the unseen to the seen. So Avogadro hypothesized that equal volumes of gases at the same temperature and pressure have equal number of particles. We say same temperature and pressure because temperature and pressure do affect gases, so we have to do them at a standard pressure. And what we later found out was that 1 mole of gas occupies the same volume as 1 mole of any gas. So 1 mole of oxygen is going to contain the same volume as 1 mole of hydrogen or helium or any other gas. All gases, if we have the same quantity of it at the same temperature pressure, occupy the same volume. This is known as Avogadro's law, or like I said, Avogadro's principle. Since he came up with this, experiment has shown that if we're at standard temperature and pressure, which is 0 degrees Celsius and 1 atmosphere, if we're comparing gases at the same temperature and pressure, that they're going to occupy 22.4 liters. This is the standard volume of a mole. How big is 22.4 liters, you ask? Thanks for asking. You can see here it's slightly bigger than a basketball. Okay, maybe if you went to the grocery store, bought one of those big pink balls or those bouncy balls, that's going to be about the size of it. So 1 mole of any gas at STP, standard temperature pressure, is equal to 22.4 liters. Write that down. You definitely need to know that and have that memorized. Okay. Now we have a relationship between volume and moles, particle and moles. Now we can jump ahead and talk about the relationship between grams and moles. And we do that through what's called the gram atomic weight. The gram atomic weight is simply how much does 1 mole of atoms of a given element weigh. And the nice thing is we can use the periodic table to figure this out. The numerical value is equal to the atomic mass that's in each square, but instead of expressing it in AMUs, we're going to express it in grams. So, for example, hydrogen, 1 hydrogen atom weighs 1.01 AMUs. Well, 1 mole of hydrogen weighs 1.01 grams. Same thing with formula weight. So if we have a compound, it's the weight of the formula is how much is 1 mole of that. So H2O, for example, we said it weighed, I believe, 18.02 AMUs for 1 molecule, but 1 mole of it's going to weigh 18.02 grams. How much is that? Remember, it's about 18 milliliters because 1 gram is equal to 1 milliliter. So you could, if we threw 1 mole of water on you, you'd feel it. You couldn't take a bath or a shower, but you definitely would feel it. Okay, so the formula, once again, is the sum of all the weights. So when we are doing atomic weights, it's very important for our class that you're going to round it 2 decimals before doing any calculations. So this is why I harped on rounding first semester. If you round your numbers wrong here, you're not going to get the correct answer. So you need to make sure that you round it 2 decimal places correctly. If you're having problems, come back and see me or go watch the other vodcasts on rounding. Okay, so oxygen, for example. If we look at the periodic table, it says 15.994. We would round that to 16.00 before we do any work. Okay, let's talk about subscripts. If we have 1 molecule of H2SO4, what that means is that we have 2 hydrogen atoms, 1 sulfur atom, and 4 oxygen atoms. Now, if we move up to moles, if we have 1 mole of H2SO4, which is sulfuric acid, by the way, what we now do, our subscripts aren't atoms, but they're moles. So in 1 mole of H2SO4, we have 2 moles of hydrogen, 1 mole of sulfur, and 4 moles of oxygen. The ratios stay the same. We're just changing our value from molecules to moles. So how do we determine the weight of 1 mole of a compound? Well, we simply add everything together. So if we have 1 mole of H2O, okay, its weight, gram atomic weight, is the sum of all the weights present. So first thing we need to do is identify how many moles of each element do we have. Well, we have 2 moles of hydrogen, 1 mole of oxygen. Then we look at the periodic table to figure out their weight. Well, 1 mole of hydrogen weighs 1.01 grams, so we multiply by 2, get 2.02. 1 mole of oxygen weighs 16.00 grams. So we add those two together and get 18.02 is the weight of 1 mole of water. Pretty simple. Okay, so that's considered to be our formula weight. All right, let's try a practice problem with something we've already talked about, sulfuric acid. First thing we need to do is figure out how many moles of each element we have. So we have 2 hydrogens, 1 sulfur, 4 oxygen. Then we're going to multiply that by their gram atomic weight, which is just the number from the periodic table expressed in grams. So we calculate this out, add those all together, and we get a gram atomic weight of 98.09 for H2SO4, sulfuric acid. So 1 mole sulfuric acid weighs 98.09 grams. Pretty simple, not rocket scientists here, guys. Okay, try this on your own. Pause this video here and then see if you can fill this up. The first column, we're talking atomic masses. So that's the weight of either a single atom or a single compound, molecule, or salt. Then we want to know how much mass would weigh and then how many particles. So pause it here, copy this down, and see if you can fill it in. When you're done, come back and I'll show you the answers. Alright guys, hopefully what you notice is that the atomic mass, or the formula mass, is the same as the mass of 1 mole. The only difference being the units. This is AMUs because we're talking single, this is grams. And all of these have in 1 mole are going to have 6.02 times 10 to the 23rd particles. Okay, so same numerical value, just different units here, which is very significant. Okay, if we have grams, that's measurable. AMUs for us is not measurable. Okay, so what we can do, this allows us now to do a bunch of conversions. We did metric conversions earlier. Well, we're coming back to this. We did taught you metric conversions, so when we got the mole conversions, you know how to do it. Okay, so we can now convert between mass, grams, number of particles, and the volume of a gas using factor labeling. Copy this chart down. This is the chart that we use. I call this the Y chart. Okay, the connection, remember, when we started out between particles and moles, is that there are 6.02 times 10 to the 23rd particles in 1 mole. Between volume and moles, well, 1 mole contains 22.4 liters, and then your atomic weight, okay, whatever your moles is, it's either the formula weight or the atomic weight. You need to memorize this chart. You really need to know this. So pause this, copy this down, and then we'll come back and we'll start using it. Just a quick note when we say particles. Particles can be a couple things. Okay, they can be single atoms. Okay, they can be a molecule. If we're talking covalent compounds, we're going to be talking molecules. If we're talking ionic compounds, we're going to call them functional units. Okay, so just be aware that when we're talking atoms, molecules, or functional units, we're all talking particles. And remember, in atoms, in all of these, are 6.02 times 10 to 23rd, either atoms, molecules, or functional units in 1 mole. So don't get confused on that. So now that we have this Y chart, we can do these following types of problems. We can go from grams to moles. We can go from particles to moles. We can go from volume to moles. Or we can, those are all one step. We can do 2-step problems with going from grams to volumes, grams to particles, or volume to particles. So these are the 6 types of problems that you will need to know how to do. And we're going to run through examples of these. I really suggest that in these next problems you pause, write down the question, and answer it. That way you're going to have these when we go to work on these in class. You'll have examples. That way you won't have to come up and ask me every time how to do them. You can look back in your notes. So let's do some practice problems. Alright, let's set a couple ground rules here for practice problems. First of all, for all practice problems, we're going to round atomic weights to 2 decimal places. Okay, so let's try this one. 3 moles of helium is how many grams? Well, the connection, if we look at our Y chart, between moles and grams is our atomic weight. So we know, we start with what we're given. That's 3 moles of helium. Do write the compound that we're talking about behind it. And we know that 1 mole of helium weighs 4.00 grams. We got that out of the periodic table. So to solve this problem, we take 3 times 4 divided by 1, and our moles cancel. We're left with grams of helium, and we find out that 12 grams of helium is equal to 1 mole. Okay, so 1 mole is equal to 12 grams of helium. Pretty simple. Let's try another one. Instead of doing an element, let's do a compound. So we have 120 grams of hydrogen bromide. How many moles is that? Well, first thing we have to do is figure out the formula weight. We do that, we know, pull these numbers off the periodic table, and we find out that 1 mole of hydrogen bromine weighs 80.91. So we start with what we're given, 120 grams, and we're going to convert grams to moles. So what we want to get rid of goes on the bottom, so we're going to put this number down on the bottom and 1 mole on top. Once again, our grams are going to cancel each other out. We're left with moles, and we do our multiplication, 120 times 1 divided by 80.91, and we have 1.48 moles of HBr. Let's try another type here. If we have 0.35 moles of magnesium, how many atoms? So we're going off the other arm of the chart where our connection is Avogadro's number. So once again, start with what you know, 0.35 moles of magnesium. We know that in 1 mole of any substance there are 6.02 times 10 to the 23rd particles. What we want to get rid of goes on the bottom. What we want to keep goes on top. So 6.02 times 10 to the 23rd atoms goes on top. Over 1 mole, our moles will cancel out, and we multiply 0.35 by 6.02 times 10 to the 23rd, and we're left with 2.11 times 10 to the 23rd atoms of magnesium. Pretty simple. Okay, try this one. If we have, let's go the other way. If we have 7.5 times 10 to the 23rd atoms, how many moles? Same connection, Avogadro's number, but we're going in the opposite. Start with what we know, 7.5 times 10 to the 23rd atoms. Okay, what we want to keep goes on top. That's going to be moles. What we want to get rid of goes on bottom, atoms. So we fill it in like this, do the math, and come up with 1.24 moles. So even though we have a huge number of atoms, it's really not that big as far as moles go. Okay, let's go to the bottom of the Y chart. Go from liters to moles. We know our connection is that 1 mole is equal to 22.4 liters. So once again, start with what you know. 10 liters of a gas. Okay, what we want to keep goes on top. That's going to be moles. What we want to get rid of goes on the bottom, liters. So 1 mole is equal to 22.4 liters. Okay, liters cancel, and we're doing multiplication. We're left with 0.45 moles. I didn't put any units after this because it was just a gas. If it would have been a specific gas, I would have wrote that there. Okay, these have all basically been one step. Given plus one step. Now let's move on to a little more difficult. We're moving 2 steps. So look at this. Grams to atoms. If you look at your Y chart, there is no direct connection. We have to go from grams to moles to atoms. So start with what you know. We know that 8.5 grams of sulfur, to get the moles, we got to look at our periodic table, and we know then that 1 mole of sulfur is 32.07 grams. Well, now we got moles, we can move to atoms. We know that 1 mole of sulfur contains 6.02 times 10 to the 23rd atoms. So take 8.5 times 1 times 6.02 times 10 to the 23rd, and then divide that by 32.07, and we get an answer of 1.60 times 10 to the 23rd atoms. Check our units. Grams cancel, moles cancel, we're left with atoms, which is what we want. Let's try another one, going from atoms to grams. Same problem, but we're going backwards. So once again, start with what you're given. Okay, well, we can't go from atoms to grams. We got to go from atoms to moles to grams. So use Avogadro's number there. Our atoms will cancel out. And now we got to go from moles of a substance to grams. So moles will go on the bottom, grams on the top. We use our periodic table to figure out that value, which is 32.07 grams for 1 mole. Multiply it. 8.5 times 24th times 1 times 32 divided by 6.02 times 10 to the 23rd, get 4.5267 grams of sulfur. Now, if you're having problems entering these big numbers, these scientific numbers in your calculator, come see me. Remember, we talked about that earlier in the year, how to do that. Okay, let's go a couple more here. Practice problems for molar volume. So we're going from liters to molecules. Okay, same thing. Start with what you're given, 15 liters. We know that 1 mole is equal to 22.4 liters. And then we want to go from moles to molecules. Well, that's Avogadro's number again. Liters cancel, moles cancel. We're left with molecules of O2. Do your math, and you come up with 4.03 times 10 to the 23rd molecules of O2. Nice and simple. Okay, our last practice problem here. Let's go from liters to grams. And notice it's talking at STP, which just means we can use the 22.4 volume. So start with what you know, 15 liters. Okay, go from liters to moles, using 22.4. And then finally go from moles to grams using the periodic table. It's N2, a Brinkelhoff one, so 28.02. We multiply it. Do your multiplication, you end up with 18.76 grams. I know I went through these problems pretty quick, but if you have questions, go back, watch a video, pause them, and do this. We are going to do plenty of practice in class, so you will get lots of practice in there. Okay, guys, so we found that the mole let us go from the unseen world of atoms and molecules up into a measurable unit. Okay, this is going to be really central to what we spend the next few weeks doing, so make sure you understand this. If you don't, come in and see me and we will practice before we get to class. Otherwise, guys, take care and I will see you in class.